So we have this thing, psi plus minus, right? Psi plus minus, right? And this is equal to phi, right? Plus something. So this is the incident wave, and this is the solution that we're after. This is the solution of the Hamiltonian. And the Hamiltonian is H naught plus V. Right? You guys remember? So H is equal to H naught plus V, where this is the free particle Hamiltonian, right? And this gives the scattering. So this thing has to be equal to this thing minus. Now the part that has the scattering in it can be written 2m over h naught squared integral d3 x prime e to the plus minus I k x minus x prime over 4 pi, and this is the Green function, x minus x. And then you have this term. So this is where we are at now. This is the Lippmann-Schwinger equation, right? And we've shown that that this thing, which includes the effect of scattering, can be written as an integral over the Green's function plus this term, right? Then we calculated the Green's function, and we found out that it's equal to this, right? This was given as a homework. And I mean, I had calculated everything. The last bit was given as a homework where we had to do the residue integral. Right? Did I do it, or did I give it as a homework? Oh, maybe, yes, I did it in the electrodynamics class, but here I gave that as a homework, right? I think that's what it is. So now we have, by the way, when I claim that this is the incident wave, how can you tell? This is the incident wave. This is the solution, this psi is the solution of this equation. Right? Where E is h naught squared k squared over 2m. K is incident, or h naught k is incident momentum. Now this is the picture. We prepare particles with definite momentum, which means that they are plane waves, right? Or they can be plane waves. And you choose them to be plane waves, which means that they're moving in a given direction, right? Things don't change in this direction, so that's plane wave. And the energy of the incident wave is this. And since the scattering is elastic, you're looking for solutions of H which has the same energy. That was the whole story. And in these solutions, you will identify the incident wave and the scattered part, and using the ratios of the currents, you will get the probabilities of scattering in a given direction. That's what the whole story is, right? Question: how do you know that this is the incident wave? This just comes in the solution of this equation, right? This is the incident wave because if you put V is equal to 0, that's all what is left. So that must be the incident wave. If there is no scattering center, then this is the only thing that you have. This is the only wave that you have. So this is the incident wave, right? If this is the incident wave, then the effect of the scattering is all here. By the way, until this point, we haven't sort of used any approximation. We haven't used any assumptions. This is the general equation. So you can just consider it as general as time independent Schrodinger equation. This is time independent Schrodinger equation for this case without any assumptions. In other words, the only thing is that we have written H as H naught plus V. When I say there are no assumptions on V. V could be anything. Okay. So now we're going to start making assumptions. We're going to solve the whole problem as in a perturbative approach, as perturbation theory. So we're going to do it, what do you call this, order by order. So we're going to have a zeroth order result, and a first order, and second order, and third order, and so on and so forth. And it's up to you. It's up to you to go to as many orders as you want. And that means that we're going to assume now that V small. That's what perturbation means, right? Okay. So V small. So I'm not going to go into what V small means. You know what it means. If you're still have some doubts, you can just put a number alpha here, and this number alpha could be small. That's a 10 to the minus 3, 10 to the minus 4. That's what it means to be small. Right? Guys? Right? Okay. So the first thing is that we are only interested in psi plus. Why? It's the outgoing wave. Why would you be interested in the incoming wave? So this is. Yeah. By the way, what is r minus r2? This is something like e to the I k r over r, right? And this is the Schrodinger wave. So plus means outgoing, minus means incoming, right? So if you want to talk about scattering, just like we had the case of one-dimensional scattering, we were not interested in the part that was going this way. We were only interested in the part that was going this way, on this side. It's the same thing. You're not interested in the part that is coming in, you're only interested in the part that is going out. In other words, this is about the initial conditions.
You have written the incident wave function. You have equated it to the incident wave function.
We have equated it to the incident wave function? The incident wave function is here.
So why have you equated it to the incident?
I have no idea what you're asking. Why have we equated it to the incident wave function? Are you asking why is there this bit in this? Why do we have this bit in here?
Why have we included only this bit? Why not the other part?
Which other part?
The one after scattering.
The one after scattering? Again, I don't know what you mean. The thing, there is, so in this picture, there is no such thing as before scattering, after scattering, right? These are plane waves. For example, solutions which exist for all time and for all space. So this is not in the wave packet approximation.
Phi is only the incident part.
Phi is only the incident part.
So
When we say that this, when we ask why this is the incident part, we know that this is the incident part because the V0, this is the only part that is left. Right? So this is the part.
So why have we equated psi to phi? Phi is only the incident part, so why have we equated this whole side?
I don't know what it is. Sorry. Really, I don't understand. So if we go back, you guys remember how we wrote psi? Psi was, how was it? 1 over T minus H naught V psi plus phi. Right? It was like this. That just comes from the Schrodinger equation. Right? I really don't understand what you're asking. This has come from this equation. So can you help me again what you're asking? What do you mean that I have equated? This is the solution. This is
the general wave function.
Yes, this is the general wave function like the one that we had written. A e to the I kx plus b over a e to the minus I kx theta of minus x plus c over a e to the minus plus I into x theta of x. Something like this, right? So, just a second. So then this is the incident part. And then once you have identified the incident part, the rest is the scattered part. Of that, this is the reflected part and this is the transmitted part. Here there is no transmission or reflection, there is just scattering, which is here. And this is the
psi plus minus includes both the incident and scattered part, right?
No. Oh yes. So I mean, maybe you are thinking that psi plus is scattered part and psi minus is the incident part? No. Or maybe the confusion is that you're thinking that you're confused about why we have chosen psi plus only. That's all. That's fine.
तो जो psi है उसमें दोनों parts होंगे.
कौन से दोनों part?
Incident और scattered.
Incident and scattered.
पिछले वाले pi वाले plus minus.
ये इसके इक्वल है ना?
ये इसके इक्वल क्यों है सर? वो तो सिर्फ incident है और वो pole है.
Oh God! इतनी देर से हम ये लड़ाई कर रहे हैं. ये माइनस है, ये इक्वल नहीं है. Really? मैंने पूरा सब कुछ दोबारा से पढ़ा दिया है. अब ठीक है? चलो ठीक है. Anyway, so this is not an assumption. This is just how the situation is. I mean, you're not setting up. So what are we saying? We're saying that if we have been working in the wave packet formulation, this is how it would look. You will have a wave packet which will be coming this way, and there will be a scattering center, which is given by the potential V. This will be the initial situation, and finally, what you would have is this is sort of a plane wave, concentrated plane wave, and then you would have something like this plus something like this. This will be the spherical wave going outward. So you don't have a situation in which you generate a plane wave which is coming inward, scatters, and becomes a plane wave. That's not what we're asking. And that's why we don't want psi minus and only psi plus. Right? So as the situation creates in which you sort of have the initial conditions where is spherical wave is coming in and it's centered at this thing, and then it goes out, scatters as a plane wave. That's not what we're doing here. That's why we're not interested in this bit. Is this clear? Yes. Okay. So the second thing, and this is an assumption now. So we specialize. To a localized potential. Right? What does it mean, localized potential? What it means is that we want this thing to be equal to V of x prime delta of x minus x. Delta q. Right? What it means is that when you are being scattered, right, you only feel the potential where you act, and you don't feel the potential from a whole neighborhood. ठीक है? आप अगर आ रहे हैं और आप स्कैटर होते हैं, तो जहां से आप स्कैटर हो रहे हैं, आप सिर्फ वहां का पोटेंशियल फील करते हैं. So there is no non-local effects here. ठीक है? Any questions here? इसकी क्या नहीं है? फील्ड में क्या मतलब? ये किसी रीजन के ऊपर डिफाइंड, हाँ एक रीजन के ऊपर डिफाइंड. हाँ, तो जब वेव आ रही है, तो अगर किसी कोई बिट जो है वो कहीं से स्कैटर होती है ना, तो वो इसी जगह से स्कैटर होती है. अगर वो यहाँ से स्कैटर होती है, तो पोटेंशियल इस रीजन का फील नहीं करेगा, किसी नेबरहुड का फील नहीं करेगा पोटेंशियल. अगर कोई चीज़ यहाँ से स्कैटर होती है, तो यहीं से स्कैटर होती है. लेकिन वो उसी जगह का पोटेंशियल फील करता है जहाँ पे वो होता है, राइट? वो पूरे एक रीजन, आप ऐसा मॉडल बना सकते हैं जिसमें पूरे रीजन का पोटेंशियल फील कर रहा है, जिसका मतलब है कि उसके जो उसका जो कांटेक्ट है, जिस जहाँ पे वो फील्ड के साथ कांटेक्ट में है, वो एक पॉइंट पर नहीं है बल्कि दूसरे पॉइंट्स के साथ वो कम्युनिकेट करें. ठीक है? सो हम जब लोकलाइज स्पेशलाइज कर रहे हैं लोकलाइज पोटेंशियल को, तो मैथमेटिकली उसका मतलब ये है और फिजिकली उसका मतलब ये है कि आप जहाँ पे हैं वहीं पे पोटेंशियल फील करें. ठीक है? ओके. So if we have the localized potential, then I can write that equations upstairs. I can write that as psi plus of x, right? And I'll soon stop putting this plus as well. If you want to just put psi of x is equal to phi of x, right, minus 2m over h cut squared d3 x prime e to the I k x minus x prime over 4 pi x minus x prime, and then this can be written as b of x prime, right, and psi plus of x prime. Is this clear? Right? How did you get this from there? कहाँ से आया? नहीं, obvious है, वहाँ से नहीं आया.
Second,
हाँ? हाँ, ये जो लोकलाइज पोटेंशियल लिखा है, अगर ये assumption ये इसको स्पेशलाइज करें तो ये नहीं बनता है. वैसे नहीं लिख सकते आप. ठीक है? अदरवाइज अगर ये लोकलाइज नहीं है, सिर्फ इस पॉइंट पे डिपेंड नहीं कर रहा, अगर और पॉइंट पे डिपेंड कर रहा है, तो फिर उनके ऊपर भी एक इंटेग्रल आएगा. पूरा एक इंटेग्रल होगा उन पॉइंट्स का जिसके साथ ये इंटरैक्ट कर रहा है. लेकिन क्योंकि उनके साथ एक ही पॉइंट के साथ कर रहा है, तो वो इंटेग्रल गायब हो जाता है. जस्ट एट दिस पॉइंट. इन अदर वर्ड्स, you can see that x v psi prime. This is just x prime b x double prime psi b x double prime, right? Like this. And so this thing is v of x prime delta of x prime minus x double prime, and this is psi of x double prime dx double prime. And when you integrate, this goes away and this goes away and this becomes x prime. Okay? That's how you go from there to there. Okay, so let's look at the picture that is emerging now. Let's look at this picture. So you have a scattering center. The scattering center, let's say it's like this, and you prepared particles that are coming this way with momentum k, right? And so this is direction k, and then you're scattered in this direction. And this is the point P where you're observing the particles, that's where your detector is. And so this thing, this direction is R or X. We're calling it X. X. And so this is X prime vector, and so this thing is X minus X prime. X minus. And this angle, let's say, is okay. Any questions? So basically, you have these vector space like this, right? And you are scattered at some point, and you go into this direction and end up at this point, right? This is R. This is the origin. There is nothing special about it. This is, let's say, the scattering center, center of the scattering whatever place, and then this thing is X, and you just, if you're scattered from here, if you're coming along this direction, you're scattered in this direction. If you're coming here, you will be scattered like this. In that case, X prime would be this, and you will integrate over all possible X primes. So that will give you the total probability of being end up there. Right? So just take one of them, and then we will integrate over X prime. So it's like this. Is this clear? Okay. So now this is a very crucial assumption, and this is realistic. It's very crucial and it's realistic. The region that generates a non-negligible contribution to non-negligible contribution is limited or finite. Is finite. You can call it limited, whatever. Why do we need this? Because we want to sort of open this up. Okay? Usually what happens is, for example, if you're doing electron-electron scattering, you're observing the electron, let's say, at a distance of a meter, while the scattering that happens is of your millimeter or micrometer. Okay? जहाँ पर non-negligible contribution जिससे से आ रही है, if the electron just goes away, sort of from the electron is here and the electron just goes away to this distance, the contribution, the effect of this electron on the other electron has died out. Okay. So the way we model that is that we'll say that the region over which we generate a non-negligible contribution to the scattering is limited, is finite. On the other hand, where you're observing it at is at infinity. Right? So now this might not be true. You might be observing it very close by, in which case this will not go through. But in general, what is happening is that, for example, in a detector, the detectors are like at this distance, something is happening here, and you're detecting the particles over here. Whereas the effective total cross section is very small. It's in bonds, which is 10 to the minus 10 meters squared. Okay? Does it make sense? Yeah. And of course, point P, this is point P, is far out. Point P is far out. Which means that X is always much bigger than X prime. Right? This thing. Or we're going to call the magnitude of X R. So R is much bigger than. Right? Any questions, guys? Questions? Okay. So, X minus X prime I did not give a homework last time, right? Did I? मेरा क्वांटम का दिया था लेकिन आप इसका
इन्हीं में होता है फार फील्ड अप्रोक्सीमेशन
हाँ
वहाँ पे करते हैं x minus x prime को करते हैं x minus n dot x prime
कौन जाते हैं अभी वो कौन जाते हैं Okay, so this can be opened up as if I have not given you the homework, remind me I have to I have the homework coming with you. So r squared plus r prime squared minus 2 r prime cosine of alpha, where alpha is this angle. Right? Square root. Or you can write it as r into 1 plus r over r prime over r prime over r minus 2 r prime over r cosine of alpha 1/2. And so if this is really small, then the square of it is negligible, right? And so this is approximately r 1 minus r over r prime over r cosine of alpha, which is equal to you can write that as r minus r so you can write that as r hat. First r prime cosine of alpha, which is r minus r hat dot x squared. Right? Is that what you're asking?
yes.
So now we're going to define. So this is the direction that we're being scattered in. So now you can see that if this thing is really small and this thing is infinitely far away, all of these vectors are actually parallel. Does it make sense? So since you have sort of enlarged it, you can sort of see that this vector and this vector are not parallel, but actually in practice they're almost parallel. Okay? So basically you have something coming like this and then something going like that. Or in other words, the spherical wave that you're measuring the spherical wave at a great distance, so there you can just see it as a plane wave. And Kevin? R जो है वो x का मैग्नीट्यूड है, x वेक्टर है, ये नोटेशन है सेपरेट की. अगर आप चाहें तो सब जगह पे I should have made my notes better. इसको हमें जो हम सारा यूज करते आए अब तक वो R और R प्राइम है, right? ये हम ये यूज कर लेते हैं, but factor uses x and s prime, and the magnitude of x is R. So ये जो मैग्नीट्यूड है ना ये R, ठीक है? So basically you have K, this is K, direction K, this is the direction, and let's call this scatter direction, KS. And this angle, and this is alpha, right? This is alpha, this is x prime. So I can also write this let's just define for the time being. Ks is equal to K. So this K is the same thing as the K over there. Okay? This is the energy, this is the momentum that you prepared the particles in. Right? And so since the momentum is not changing, only the direction is changing. So I can write Ks, this Ks, which is the scattered momentum, as K R. Whereas initially K is K Z, let's say, or K whatever direction that this direction is. Okay. So if we come back to this part, right? This part, and look at this calculation, this thing can be written as e to the I plus e to the I k r e to the I minus, because of this minus sign here, ks dot x prime, right? And divided by 4 pi r. So for the denominator, I'm just taking this to be r. So if you plug that back in, under all of these assumptions, psi plus of x for large r, right, these two included. So we can write this as this: x k, this is the incident field, okay, minus 1 over 4 pi 2m over h cut squared e to the I k r over r d3 x prime e to the minus I k s dot x v of x prime psi of x prime plus. Agree? And this whole thing is equal to, so now I'm going to bring out this factor of 2 pi 3 over half. This thing is e to the I kx, right? In fact, k dot x, and this factor out. Right? This whole thing is e to the I kf divided by 2 pi 3 over half. That comes out. And this thing is 1 over 4 pi 2m over h cut squared, a factor of 2 pi to the power 3 halves, coming from here. Right? I've taken that out. So you get that. And Yes, and you want a factor of, so e to the I kr over r d3 x prime e to the minus I ks dot x over 2 pi 3 halves. So then this becomes 2 pi cube v of x psi plus of x prime, right, this thing. And if you write this equal to 1 over 2 pi 3 halves e to the I k dot x minus plus e to the I k r over r f of k s k. Then, you see what I'm doing? I just made a mess there. Let me write it. So, again, psi plus of x goes to 1 over 2 pi 3 halves e to the I k dot x plus e to the I kr over r f of ks. Then f of ks k, this thing is minus 2 pi cubed over 4 pi 2m over h cut squared d3 x prime e to the minus I ks dot x prime over 2 pi 3 halves v of x prime psi plus. All of this category is here. That's why we separated this out. Okay? The rest of scattering will just be how to sort of approximate this thing. Okay? By the way, you can see from here, what can you see? This is the plane wave, which is the incident wave, because if v were 0, then this would be 0, this would all that would be that way. And this is the spherical wave with this amplitude. So the amplitude depends on what state that you have prepared in for the incident wave and which direction that you're measuring the scattered particle in, right? Where have you put your detector at? So it will depend on these two things. So this is the amplitude of this wave. And later on we'll show that this is just the scattering cross section that we have. We're always after the scattering cross section, right? Differential cross section. So this will become the differential cross section. Anyhow, so by the way, since this thing is going to appear again and again, let's give it a name. What do you want to call it? Beta? Alpha? Let's call it A. A, capital A. Okay. Let's call it capital A. Yes, one more thing. You should also see that this thing is equal to minus or just A Ks V psi plus. We will have a chance to use this equation later on. This whole thing is just this. You want to see how, or you can see it's clear obviously, right? If you just put a 1 here and a 1 here, that will give you psi of x. This will give you this part, and ks into x will give you this part. Right? Remember that k prime is delta k minus k prime, and x k is e to the I k dot x over 2 pi LUMS. Right? So we can see that this thing is equal to this. Guys, any questions? ये तो ऐसे बता रहे तो डेफिनेशन बता रहे ये किसी भी चीज के लिए ट्रू है। कोई सी दो आइगन स्टेट्स हो मोमेंटम दिस इज ट्रू, ठीक है? वो बात की बात है कि ये क्या है, ठीक है? Any questions? क्या कारण? नहीं, मैं कह रहा था अगर आप सब इस चीज को देखें, राइट, तो जब आप मुख्तलिफ वेव्स को इकट्ठा करते हैं तो साथ उनका क्या होता है, उनका एम्पलीट्यूड होता है, ये एम्पलीट्यूड। सो बेसिकली अभी देखेंगे कि क्या था, अभी हमने बात कर रही, राइट? लेकिन अगर आप सिर्फ इसको देखें तो ऐसा लग रहा है कि जैसे ये एम्पलीट्यूड है इस वेव का, इसके साथ ये k है और ये k को डिफाइन करते हैं उसका एम्पलीट्यूड। दिस इज इन जनरल कॉम्प्लेक्स नंबर। अब बेसिकली जो चीज हम कैलकुलेट करना चाह रहे हैं वो तो डिफरेंशियल क्रॉस सेक्शन। सो द डिफरेंशियल क्रॉस सेक्शन इज दिस। सो ये निकालना चाहते हैं ना, बिकॉज दैट्स वेयर द थियरी एंड एक्सपेरिमेंट मेक कांटेक्ट। तो ये है क्या? ये है 1 over L, राइट, Vn over d सिग्मा, राइट? हमने देखा था कि जितने पार्टिकल आपको पर यूनिट एंगल मिल रहे हैं किसी डायरेक्शन में, अगर आप उसको डिवाइड कर दें टोटल पार्टिकल जो आपने भेजे थे उस डायरेक्शन में, तो ये प्रोबेबिलिटी है स्कैटरिंग की उस डायरेक्शन में, राइट? इन अदर वर्ड्स अगर आप इसको ऐसे लिख लें d theta phi d omega, so then this is just the number of particles that you're getting in d omega in this direction divided by the total number of particles. ठीक है? Any questions? So if let me write this down in words. Number of particles scattered into d omega per unit time blah blah over number of particles incident on the target per unit area per unit time, right? ये चीज किसके इक्वल है? ये चीज है जो भी आपका ये करंट है इस डायरेक्शन में, जो भी करंट है टाइम्स d ओमेगा, राइट, टाइम्स द एरिया, सॉरी, तो r स्क्वायर d ओमेगा। और ये चीज किसके इक्वल है? j इंसिडेंट। ठीक है? एंड दिस थिंग अगर आप इसको कैलकुलेट करें, अब आप यहां पर वापस आ जाइए, ये चीज देख रहे हैं आप, ये है इंसिडेंट और ये है स्कैटर्ड, ठीक है? अगर तो यहां से आप जे स्कैटर्ड कैलकुलेट करेंगे, यहां से आप जे इंसिडेंट कैलकुलेट करेंगे। तो इफ यू डू दैट व्हाट यू विल गेट इज hk over mr squared into r squared d omega divided by hk। ये ks है लेकिन उसका मैग्नीट्यूड सेम है, so I'm just writing it hk over। Guys, any questions? Oh sorry, यहाँ पर आएगा f of ks k Okay?
R square d omega.
R square d omega is the area of the detector. ठीक है ना? आप जितना एरिया डिटेक्टर का बड़ा करते जाएंगे आपका नंबर ऑफ पार्टिकल ज्यादा मिलते जाएंगे. So this will cancel with basically this will go away with this, and what are you left with? You're left with f squared d omega, which means that d of theta phi is just f k s k squared. Guys, so the probability of going into a certain direction is just the amplitude. This was the amplitude, so the square is the probability. Right? Okay. हाँ तो के एस का मैग्नीट्यूड के ही है ना, यहाँ पर तो मैग्नीट्यूड आएगा ना. ये हम इसका मैग्नीट्यूड ले रहे हैं. ठीक है? ओके. तो अगर आप अब आप सब चीजें भूल जाए, अगर आप इसको कैलकुलेट कर सकते हैं और इसको हम कैलकुलेट करेंगे परटर्बेशन फीचर. अगर आप इसको कैलकुलेट कर सकते हैं f को, then you just know what differential cross section is. If you know differential cross section, you know how many particles you should be receiving at your detector in what direction, and so you can make contact with these particles. Guys, make sense? Right. So again, let me write it out. F of ks k, right? This is equal to a d3x prime e to the minus I ks dot x prime over 2 pi 3 half d of x prime psi of x prime. So, if you guys remember your perturbation theory, how do you do it? आप successive approximations करते हैं. पहली approximation में आप कहेंगे जी कि v0 है. If v0, then psi is just equal to phi. Then psi is just phi, right? फिर आप वो phi लेंगे और इसमें psi की जगह put कर देंगे. That will give you the first order solution. फिर जो भी साइन निकलेगा वो दोबारा इसके अंदर डाल देंगे तो सेकेंड ऑर्डर सॉल्यूशन. राइट? द फर्स्ट ऑर्डर इज गोइंग टू बी एक्सट्रीमली इंपॉर्टेंट फॉर द एग्जाम एज वेल. ठीक है? सो what is the zeroth order? So if you solve this by perturbation theory, zeroth order solution is going to be psi is equal to phi. Psi of x is equal to phi. So incident, which is just e to the I k dot x over 2 pi 3 half, right? And in that case, f of ks k is 0. First order. The first order is that psi of x is phi incident of x minus a or plus a e to the I k r over r d3 x prime e to the minus I ks dot x over 2 pi 3 half V of x prime, and now instead of psi, we have phi incident. Now this can be solved because you know what phi incident of x is, right? So what I'll do is erase this and instead put e to the I k dot x prime over 2 pi p x. Let's solve this. In fact, if you just look at it, this becomes I k minus ks x prime v of x 2 pi q. And so f1 of ks k, this is equal to minus 1 over 4 pi 2m over h cut squared d3x prime e to the I k minus ks x prime d. So now we cannot go any further unless you know what d of x prime is. अच्छा वैसे है क्या? What does this look like? This whole thing. This is very simple. This is extremely simple. First order differential cross section is equal to just the Fourier transform of the potential. That's it. You just take the Fourier transform of the potential and it tells you what those f's are, what the amplitude is in a given direction. Okay? Make sense? Now this is going to be really important. So let's take an example and let's try to put it in a simpler form. Okay, so now what we're doing is trying to put this in a simpler form, and I'm going to show you that this can be real. This can always be real. So Q, let's define Q, which is K minus Ks, which means that the magnitude of Q is magnitude of K minus Ks. So if this is Ks, right, this is K, and the two have the same magnitude, same length, and this is Q, right? And this, if this angle is theta, then you can see that Q is, the magnitude of Q is 2K sine theta over 2. Okay? Make sense? By the way, so all of the information about the energy and the angle is in this K, in this Q, at least at this level. Okay, so F1 of some theta naught in some given direction. So again, we're assuming that the target is absolutely symmetric or spherically symmetric. So it's not going to depend on, things are not going to depend on phi.
What is theta?
Second?
What's theta?
Theta is this angle. Theta is the scattering angle. The way that we had initially defined it. Theta is the scattering angle. Excellent question, yes. Theta is the scattering angle. नहीं अल्फा नहीं है स्कैटरिंग एंगल, अल्फा के तो आप सम कर रहे हैं, सम कर दिया आपने, खत्म हो गया। ये जो एंगल है ना इसकी बात होगी, ये एंगल है थीटा, ये एंगल थीटा है, या आप चाहें तो ये एंगल थीटा है असल में, लेकिन ये पैरेलल है तकरीबन से। So this thing is minus 1 over 4 pi 2m over h squared, and now you can integrate from 0 to infinity. What I'm doing is that I'm going to open up this integral over this, right? This is a given. ये fixed है, a minus b prime is fixed, right? Once you fix the angle, so this is fixed. So what I'm going to do is r prime squared dr prime minus 1 to plus 1 d cosine of theta, right? E to the I q r prime cosine of theta, right? So the magnitude of x is r prime. And 0 to 2 pi d phi. Okay, so this is going to be where is B? B to गया? मेरा ये नोट्स यहाँ पर आ गए थे B of X. So since we're talking about spherically symmetric, so this just becomes B of R. Okay? Otherwise, you won't be able to do this again. Anyway. So this thing is well. Let me, since we have to go to the talk as well, so let me give you the rest of the homework. You just do this integral, right? This is very simple integral to do, and you will get the answer 1 over q 0 to infinity r prime sine q r prime v of r prime By the way, this is a function of theta now. I want to just, where is the angle here? Q. Right? यहाँ पर आपने इसके ऊपर इंटीग्रेट कर दिया, तो ये कैसे बचा पीछे? कैसे बचा? हैं? ठीक है, क्या कह रहे हैं? ठीक है। हाँ, क्यों? जब एंगल के ऊपर इंटीग्रेट कर दिया तो फिर एंगल कैसे बना? दो एंगल है। हाँ, दो एंगल है बीच में। ये वो एंगल नहीं है। ये जब आप प्राइम के ऊपर जब सम कर रहे हैं ना, तो ये जितने भी आपने स्कैटरिंग सेंटर है उसके ऊपर सबके ऊपर इंटीग्रेट कर रहे हैं। जबकि आप एक गिवन डायरेक्शन में आप कैलकुलेट कर रहे हैं कैप्टीट्यूड के, ये वो चीज़ है। ठीक है? हाँ, this is theta. Okay, let's stop here. We'll do an example tomorrow, and we'll try to calculate the Rutherford's scattering formula, whatever you call that. Rutherford scattering formula. It'll become more transparent. Okay, so any questions?